Hello, everyone. My name is Xander Wang, and I am an assistant professor in the School of Climate Change and Adaptation at the University of Prince Edward Island. So today I'm very glad to co-host this session with Resea Razavi from Western University. So I will turn this to Resea for a brief introduction, and we can get started.
All right, hi everyone. My name is Resea Najafi, and I'm an assistant prof in the Civil Engineering Department at Western University in London, Ontario.
Yeah, thanks, Resea. So today we will have 5 presentations in our flood session, and the first one will be an invited session presentation from Dr. Saman Razavi from University of Saskatchewan. So Saman, please go ahead.
Thank you, Xander. Hello, everyone. As Xander said, my name is Saman Razavi. I'm associate professor at the University of Saskatchewan. I'm very glad to be here. And before I begin, I'd like to thank Xander Wang and Resea Najafi for the invite to give this talk. And also my colleagues who have contributed over the last couple of years to the ideas and contents of this talk. So I'd like to begin with a story, actually a series of real events that caught my attention and I followed closely in early 2019 when the convergence of a very active monsoon and slow-moving tropical low-pressure system created unprecedented rainfall for Australia's North Queensland coast in January and February. And it was after a long, hot and dry period, and perhaps like every year, the Ross River Dam there was filling in January to store water to meet demand later in the year. Then this unprecedented rainfall hit, and with more than 1.1 meters of rain in a week, dam got filled very quickly and reached the emergency level. And the operators ended up fully opening all the gates for dam safety issues. Here I'm including some links to some interesting videos about this event and the impact, if you had interest to watch later. So what happened next? The city of Townsville got flooded, resulting in 5 casualties and more than 1.2 billion in property damage. And of course, significant indirect costs and consequences that are always hard to quantify in monetary terms. Of course, the public reaction was serious. I'm quoting, for example, from The Guardian that some residents have expressed anger that water was allowed to build for so long rather than being released more steadily during the previous week of continued heavy monsoonal rainfall. And you know what? As a result, dam management went under a scrutiny. So the situation escalated and became political to a point that involved the Premier of Queensland. But quite interestingly, having observed this series of events, the key message for me as a hydrologist and water resources engineer was that the Australians questioned questioned flood management of the Ross River Dam, even though the operational protocols were up to date and followed. And basically, the emergency action plan was updated in 2018, in which floods similar in magnitude to the 2019 flood had been analyzed. So I think there's a gap here. You'll need to give me a second because my computer is frozen. Anyhow, this has been a common story and not unique to the Townsville flood, really. For example, the combination of heavy rain and melting snowpack in the Ottawa River Basin, which is regulated by a series of reservoirs, produced record-breaking flood peaks in the Canadian cities of Ottawa and Gatineau and surrounding communities in April 2019. It resulted in one fatality, more than $200 million in insured property loss, 6,000 homes flooded, and more than 10,000 people evacuated. And similar to the Townsville flood, there was a lot of public concerns around the operation of reservoirs in this basin and some conspiracy theories. And as a result, reservoir operation went under scrutiny. In May 2019, record-breaking spring floods also occurred across the Mississippi River and its tributaries, a heavily managed water system in the United States, causing 4 casualties and more than 12 billion in damages. And local residents blamed the US Army Corps of Engineers for the mismanagement of hundreds of reservoirs in this basin, being particularly critical of opening Keystone Dam and releasing a large amount of water into the Arkansas River, which had a severe impact on the city of Sand Spring, Oklahoma. And in March and April 2019, 3 massive rainfall events created flash flooding across 25 of Iran's 31 provinces, where major rivers are managed by dams and reservoirs. These events caused 76 fatalities and more than 2 billion in damage. Many Iranians wondered why the many existing dams and infrastructure were unable to protect them from these floods. And in all these 3 cases that I just showed, public discourse about these events centered on the efficacy of infrastructure design and management, and the operational rules that govern day-to-day decision-making. And the point here is, these real-time operational concerns arise from deeper, more fundamental issues associated with infrastructure planning and design, human settlement in the floodplain, and perceptions of risk. So thinking about those issues, a few of us got motivated to write a small piece around what we believe are the major challenges in face of the flood risk in an era that human is a dominant agent on Earth and has a lot of control on flow regime, flood control, and floodplain management. I think it's now well known that the magnitude and frequency of flood hazards are changing in a deeply uncertain manner due to combined effects of many different natural and human drivers. Runoff generation and river routing mechanisms are changing in a variety of ways due to urbanization, land use and cover change, artificial drainage, river training, and so on, as well as climate warming effects such as changed regimes of snowmelt, rain and snow events, and so on. On the other hand, dams and reservoirs, while perceived to modify stream flow regimes in known engineered ways, often add significant uncertainty to flood risk. Their operating rules are typically confidential and can be ad hoc at the time of crisis to address emergency issues such as dam security, that just happened in Townsville flood. And because of all the non-stationarities, there is profound uncertainty in trend predictions. And the stationarity-based notion of return period, which remains the basis for floodplain analysis and resulting flood insurance measures, seemed to have become of limited help. And basically, recent research efforts to enable traditional stationarity-based risk assessment programs to account for such predicted future trends are of limited use because they're unable to capture such deep uncertainties and complexities involved. They are actually like a more modern version of traditional deterministic safety factors that they've been using for decades in engineering work to compensate for unknown or lack of information. And having said those, the classic flood risk analysis paradigm based on the best guess estimates of how the future might look like might be obsolete in the face of radically uncertain climate change and environmental and societal changes as well. So in addition to those uncertainties, we have to be dealing with challenges around complexity of the flood risk problem itself. There are always significant high dimensional trade-offs such as upstream versus downstream water demands, flood versus drought protection, economic growth versus environmental production, and so on. However, engineering-based cost-benefit analysis methods focus only on a small subset of these dimensions and often ignore the rest. So the natural, engineered, and social systems are interwoven, we know that, in complex time-varying ways connected through different feedback mechanisms that are often hard to quantify and model and predict. And such interdependencies can result in cascading or undesired spin-off effects that are ignored in traditional engineering approaches. In addition to direct material costs, social damage costs, including public unrest, loss of lives, and long-term adverse effects on mental health, are typically excluded from economic impact assessments because these are very hard to quantify in monetary terms. And all of these are further complicated by the time-varying nature and perceptions of risk at individual, community, and institutional levels. These challenges are linked to socioeconomic interests, the development and evolution of which may be unpredictable, and affected by memories of prior floods and drought disasters, and professional and social media contents like Facebook, Twitter, and so on. So with all those challenges, where we are headed? There is some recent recognition that the flood research paradigm needs to change based on the following three fundamental underpinnings. We need transdisciplinary modeling and assessment frameworks to represent dynamic interactions, feedback mechanisms in modeling beyond traditional hydrological and engineering only based approaches. And such assessment frameworks need to allow for different levels of abstraction that can facilitate knowledge exchange and co-creation across disciplines and scientists and practitioners with different backgrounds. We also need to move from predictions to scenarios. Given that we have limited predictive power arising from deep uncertainties and profound complexities involved that I just briefly mentioned, the concept of flood probability and exposure need to be redefined to accommodate a range of alternative scenarios instead of focusing on best guess estimates. And of course, there are various tools already available, such as sensitivity analysis to identify the dominant controls of flood systems and decision-making under uncertainty that can help us make better, robust decisions in face of uncertainty and trade-offs. We also need to build more science public interfaces to boost broad participation, effective communication, and knowledge co-creation with public and stakeholders. And that is becoming more and more known in the face of these recent events. And this can only be achieved by building publicly accessible interfaces with state-of-the-art visualization techniques. So with that introduction, in the rest of this talk, I'm going to give two examples of what we are doing in my team in those directions to deal with uncertainty, complexity, and trade-offs. The first one is on integrated modeling of hydrology human systems under uncertainty in future climate. And the second one is on our efforts to understand policy dynamics to flooding events, in response to flooding events for better planning and adaptation, with some taste of social sciences and with work collaboration with social scientists involved in this field. So from hydrology to integrated human hydrological systems modeling. As some of you might know, most of our hydrologic modeling efforts are with the mesh land surface hydrology model. And you can find, of course, the details of this model in many references. I'm not going to get into details. What I'd like to highlight here is our work to integrate the hydrological model that simulates the natural processes with a water management model that simulates the engineering processes like reservoir operation, diversion, and irrigation to have a seamless integrated modeling platform for both natural and human systems. So how do we do it? We have come up with two different approaches. In the first one that we refer to as the point-based approach, we look at the operation of each single reservoir and develop simple storage release rules for different zones in a reservoir. in a way that they emulate the actual operation of the reservoir. So this is a good, very efficient approach, but with the caveat that the operation of each reservoir is modeled independent of the other reservoirs. But yeah, it has shown a lot of promise, at least in simulating the Canadian watersheds. In the second approach, we take a systems approach and emulate the operation of each reservoir in harmony with the operation of the other reservoirs, with the data use of with significant data and the use of formal water management models like ModSim DSS. This approach is, of course, much more data demanding and more computation intensive, but it results in a higher fidelity model. And in practice, because the systems of reservoirs are coordinated, this is a good approach to basically simulate what might happen in the future of these systems. And here is an example of our work of the model that I just explained for the Bow River Basin in Alberta upstream of Calgary. We have set up the mesh model with the 4x4 resolution and parameterized it by the GRU approach, group response unit approach. We particularly paid attention to the slope and aspect for this parameterization to better represent the mountain hydrology and snows and snowmelt processes in the mountain. And you might know that the uncertainty in the historical forcing data, particularly in precipitation, is a major issue in Canada. And to address that, we have used the WRF or Weather Research Forecasting model with a 4x4 kilometer resolution to allow the simulation of the convective storm. And here is an example of the model performance with the WRF input for a gauge on the Bow River at Banff. So the model performance, as you see, is reasonably good with an NSE Nash-Sutcliffe efficiency of 0.81 in calibration and 0.87 in validation. It generally does a good job in reproducing both high and low flows, and it almost captures the 2013, that big flood peak, which is a really hard job to do. So when we've developed this model, then we of course tested or used it for climate change impact analysis, and here is some preliminary results based on pseudo global warming dynamical downscaling using, again, the same convective permitting 4-kilometer WRF model. According to this projection, the annual precipitation will increase by 13%, average temperature will increase by more than 4 degrees Celsius, and the rainfall total precipitation ratio will increase from 0.3 to 0.46. And as a result of all these, the average runoff will increase by 18%. And now Zelalem is in the process of polishing these results, and it's going through a lot of refinement stages and looking at other attributes of change, like in flood peaks, and more on this study will be available in near future. So, is it all good, or we are missing something? Let's look at the cascade of uncertainty in CMIP5 ensemble projected changes in seasonal precipitation for Nelson River Basin, Canada, where the Bow River Basin is a part of. So we are now looking at the uncertainty due to the choice of RCMs and GCMs, and also the internal variability in each GCM for 3 different time periods in the future. The point here is that the change in average summer precipitation can be a wide range, basically ranging from minus 45% to plus 15% in the last 20 years of the century. And similarly, for average winter precipitation, it's projected to be in a wide range of uncertainties, somewhere between minus 4% to plus 40%. These are very large uncertainties to deal with when you want to work in adaptation or basically flood risk management. And also, what about possible changes in the intensity and duration of precipitation? it will be hydrologically different if we get a precipitation uniformly over a long period, or if we get the same amount of precipitation over a short period. In the first case, we may hardly get any runoff, but in the second case, it may result in a flash flood. So to characterize and investigate that, here we are looking at the change in transition probabilities, for example, of a dry day following a dry day, and a dry day following a wet day. And on the plots, we're comparing historical transition probabilities and those from the RCMs based on 2 different RCPs. Clearly, there are some differences in transition probabilities when we move from the historical transition probabilities, the light blues here, to the projections by the different models for different months. So we see some major differences in some months, for example, in June, July, and August. Also in winter, but in some other months, they remain pretty similar. The point is, such changes have been typically ignored in climate change impact assessments, and we need to look into them. So how do we account for those uncertainties, like in, as I said, transition probabilities or changes in seasonal precipitation? We are using a weather generation approach by which we generate thousands of plausible future scenarios by perturbing 4 different climate attributes in their feasible ranges. So the attributes of interest in our work are summer precipitation, winter precipitation, annual temperature, and the number of days, number of dry days in a year as a surrogate for transition probabilities. And once all these weather scenarios are generated, we feed them into a hydrologic model to assess the impacts on flows. So here is some preliminary results for the same basin that I showed earlier, Precipi River at Banff. I should note that we are now dealing with a 4-dimensional space, basically 4 attributes and 1 response. That is, for example, the average flow. For simplicity here, I'm now showing only a few cross sections of this 4-dimensional space, this contour plot, basically, that we refer to as the exposure space, which shows the percentage change in average flow as a result of percent change in winter and summer precipitation, for example, from -20% to +50%, and here from 50% to +20%, just based on the information we received from the CMOS ensemble. So of course, both winter and summer precipitation directly control the amount of average flows, and average flow can increase by more than 30% or decrease by -40% as a result of change in winter precipitation. And what I'm showing is based on basically emulating the number of days in historical records, transition probabilities extracted from it. And now we can do similar analysis on the other properties of, we can do, and the plot to the right, we're looking at the impact of change in the number of dry days, basically when we emulate the transition probabilities in RCM5, RCP 8.5, to tell us about the change in intensity and duration of precipitation. And what we see is pretty major change in average flows, particularly when the change in precipitation amounts are positive, right here. And we can get as much as or more than 40% increase in average flows. Of course, we can do similar analysis on other properties of the flows, like the 10-year flood or low flows, but for the interest of time, I will skip them and refer to the paper by Keshavars et al. That is now being drafted. So the last piece, I'm going to give you an overview on our efforts to understand policy dynamics in response to flooding events. And we've been collaborating on this with the International Association of Hydrological Sciences, Pontaré Working Group. The idea is to collect case studies of paired flood events that are floods in the same catchment that have happened in different times, to assess change in the number of flooding in a number of flooding indicators between the two events in time. So we have contributed to relatively recent case studies from the Ottawa River Basin and Assiniboine River Basin that I'm going to give an overview of. Here are the main indicators that we looked at associated with flooding and categorized into 5 main categories. I won't go through all the indicators here, but note that the indicators include both physical characteristics of the flood, like in hazard category, as well as policy and social dynamics in several other categories that impact flood risk. So we sought out evidence for each of these indicators in each region and measured the change in these indicators between the two events in the 2 Canadian case studies. And the idea of this initiative is to do this for a large number of case studies from all around the world, and through comparative analysis, look for broader patterns that can inform scientists and policymakers. So we're looking at if a particular attribute has changed, or if the change is small or large. And also, when you see in my plots some hollow arrows, it means it's based on limited evidence. We couldn't find a lot of evidence in the literature, but some of them are solid, meaning there's a lot of evidence to support our assessment. And here is a summary of our finding for the Ottawa River Basin case study. So we looked at the most recent major flood events in 2017 and just 2 years later in 2019. You'll note that a lot of the arrows indicating change are hollow. That means the evidence was limited in a sense that there are a limited number of scientific publications or impact studies done so far. And it makes sense because the events are fairly recent. Nevertheless, the results are quite intuitive. Event severity was slightly increased due to antecedent conditions, mainly in the second event, and the exposure and impacts also went up slightly accordingly. Vulnerability reduced though, and this is primarily because 2017 event was very recent. Before that, an increased awareness and experience was still quite recent by 2019. And looking at the Assiniboine case studies, we looked at 2011 and 2014 floods. The prior flood was more severe, mainly because the duration of the event lasted up to 3 months in some areas, even though both were similar in terms of flood peaks. The big story is the increased vulnerability between the two events, because 2014 flood was unique in modern records for the basin, arising chiefly from major summer precipitation events. So through this experience of looking at each indicators in depth, we made a few observations, and the one main one is that the compared to historical events to each region, the nature of these recent events are changing. In the case of Ottawa River Basin, both recent flood events are relatively worse than the previous historical events, even though flood management regimes are considered advanced. For Assiniboine, the region is quite used to frequent flooding events, and after 2011 damage, they brought along several changes in infrastructure and management too. But the 2014 event was unique in terms of the timing. It happened late in summer, so it was unpredictable for the people or flood risk managers. And in both cases, the commonality was that the impact has gotten worse from the first flood to the second, which is quite important to consider. So to bring everyone home and to, before I finish, just a bit of global context. The thing is, the frequency of disastrous flood events has increased significantly over the past few decades, to the point where flood is now the most common type of natural hazard. And the increasing severity of disastrous floods, particularly in regions where flow regimes are heavily engineered and regulated by many dams, reservoirs, and other infrastructure, like the case studies that I just reviewed. This challenge current science policy paradigms with respect to flood risk and undermine public trust in flood management. So here is the key message I want to leave with you. Recent flood events suggest that science and society are ill-prepared for the difficult decisions that lie ahead as the flood events and the impacts of the Anthropocene unfold. These decisions require a new science policy paradigm that grasps and systematically accounts for the uncertainties and complexities associated with future flood risk. Thank you very much.
Thank you very much, Saman. That was a very interesting and insightful presentation. Are there, if the audience has questions, you can either use your mic or type it in the chat box. In the meantime, I just want to ask a question myself. So you gave interesting examples in the beginning, Saman, that we have a reservoir system already located in a place. They flood based on their operation curves. They decide whether to keep the water or release it. But recent events have shown that things that we have observed, there is a dry condition, they keep the water and there's flood. So also you mentioned that they had updated their reservoir operation very recently. So I think that it means that they have already included climate change. They have already included scenarios, a range of possible changes in the future in their analysis. And you touched on several aspects that are very crucial, like updating IDF curves, the consequent, the wet dry events, dry events, etc. Which ones do you think were most responsible for such flood events that cause public mistrust in their system, and something that for example, the Australian government and other governments didn't really include in their operation?
Yeah, thanks for that very challenging question. I don't think I have a concrete answer for that. And you know, the thing is, this is a complex, wicked problems, as social scientists call them. Of course, the study was, or the emergency plan was pretty up to date, but the problem was probably they just followed what the engineers do, classic engineering approaches for flood risk management, which is probably obsolete. And you know what? I think public trust is a major point here. And as I said in the talk, we need to have science policy or public interfaces so we can educate people also about all the challenging problems that scientists, policymakers, managers, city planners have. And it doesn't mean that someone did their job wrong. This is just the nature, the complexity of the problem that needs to be accounted for. So I would say there is no easy solution and one size fits all solution, but the point is public needs to get more involved in all the processes and be aware of what's going on. And just on the Townsville Reservoir, I wanted to point out that that dam was built primarily for flood protection back in 40 years ago or so. But over time, it created this exposure, or the exposure products that people just basically got a false sense of security, and they approached floodplain more and more, and they built and invested more and more. While over time, they didn't notice that the purpose of that reservoir gradually shifted to water supply rather than flood protection. So then that dam became the major source of water for this city. And all these changes, they're basically hidden even to a lot of policymakers or planners. And all of a sudden, this flood hit, the dam was there for water supply, for storing water to be used later in the year, but it didn't serve the primary purpose of it that it was built for.